Okay, so I realized the other day that not everybody probably has the same chemistry background or even the background that we might need to cover some of the chapters that come later. So I know this looks like a topic that you think, oh my God, it's going to bore me to tears. But I promise you, we're going to do something really different with chemistry today. I'll go through a few minutes of basic stuff just to get everybody on the same page. But I want to show you a kind of cool example of how just the most fundamental knowledge of chemistry can allow you to do some pretty cool science stuff. So we will start with this, just the very, very basics here. Okay, let's go back to the very beginning when it comes to chemistry and look at how atoms are put together, because chemistry is really the study of atoms. A couple of terms that most of you probably know. Atoms consist of a number of what are called subatomic particles. We have protons. Protons have a positive charge, and protons are the subatomic particles that are found in the nucleus or in the center of the atom. So here's a little diagram of an atom down here. The green circles with the P are protons, positively charged. Neutrons are also found in the nucleus. They're neutral, no charge. And then most atoms are surrounded by a number of electrons. Electrons are found in discrete orbits. Now, if you really get into chemistry, something that you can study in later classes, something called quantum mechanics, which I'm sure you've heard of. How many of you have heard of something called a quantum leap? Do you know what that really is? Something about quantum mechanics that's really interesting in chemistry is that electrons can jump from one orbit to the next and back and forth. But what's really cool and what a lot of non-chemists don't understand is that, let's say this electron right here can go to this orbit, but it can never be in between. As it moves from here to here, it's never in between. That's what's called a quantum leap, to go from one place to the other without ever being in between those two places. It's kind of cool. It's not something that we really think about. For me to go here to the back of the room, I have to go in between. Electrons don't have to do that. They can actually leap from one place to the other and never be in between. So it allows for all sorts of kind of cool possibilities for how things can move around in nature. Okay, atomic charges. This is something that's actually pretty important in geology, especially when we start talking about minerals, is that atoms are typically charged in nature. They're imbalanced with respect to the number of positively charged protons and negatively charged electrons. Now, you can have neutral atoms in nature where the number of protons equal the number of electrons. The positive charges cancel out the negative charges. They do exist, but in geology we talk about ions a lot. Ions are charged atoms, and they happen when you have an imbalance of protons and electrons. Cations are when you have positively charged ions, positively charged atoms, and the number of protons is greater than the number of electrons. And anions are when you have an imbalance where you have more electrons than protons. Okay, so a few simple concepts and terms. Ions, charged atoms, cations are positively charged, more protons than electrons. Anions are negatively charged, more electrons than protons. Any questions so far? I'm sure you've all seen this before. Okay, a couple of definitions. An element. You've all heard of elements. Elements are actually really simple. It's all atoms with the same number of protons. That's all that matters. Doesn't matter how many neutrons are in the atom, doesn't matter how many electrons. All that matters in the definition of an element is how many protons it has. For example, every atom that has just one proton is called hydrogen. It doesn't matter how many neutrons are there. It doesn't matter if it's an anion or a cation. All that matters is that it has one proton. If it has one proton, it's hydrogen. Everything with one proton is hydrogen. Everything with two protons is helium. Doesn't matter how many neutrons, doesn't matter how many electrons. That doesn't factor into the definition. Everything with 8 protons is oxygen. And so on. We have over 100 different naturally occurring elements out in nature. Gold, lead, cadmium, copper, bismuth, neon, argon. These are all different elements, and it's defined by the number of protons. Now, you've heard of the term isotope. You can think of isotope as being a variety of elements. It's an element where the number of neutrons varies. I'll give you some examples here. How many protons in oxygen? 8. Always 8. Never changes. Anytime you have just 8, you have oxygen. Well, we have a couple varieties of oxygen. We have a variety, or an isotope of oxygen called O16. 16 refers to the number of particles in the nucleus. Okay? So whenever you see this little number next to an element sign, that refers to the number of subatomic particles in the nucleus. 16. Oxygen, we know, has 8 protons, right? So how many neutrons is it going to have? 8. That's the most common variety of oxygen that's out there. You're taking in breaths of air right now. The vast, vast, vast majority of the oxygen in the air you're breathing is O16. But with every breath, you're getting a couple other varieties of oxygen too. You're getting one called O18. It's oxygen, so it still has 8 protons. But now it has 18 particles in the nucleus. So it requires that you have 10 neutrons. And you might think, yeah, well, so what, big deal. Actually, these behave really different in nature. They have different melting points, different boiling points. Some of this stuff we'll talk about. You've heard of radioactive isotopes, right? These are things that spontaneously break down in nature. Give you some other examples. Hydrogen. The vast majority of hydrogen that you find out in nature is just a proton. That's all it is. One little tiny proton. It may have some electrons around it, it may not. Doesn't matter. One proton is hydrogen. If you have H1, are you going to have any neutrons? No. But we do have some varieties of hydrogen that do have neutrons. We have H2. 2 particles in the nucleus. One has to be a proton to make it hydrogen. So you have 1 neutron as well. We also have another variety called H3. Sometimes this is referred to as tritium. It's just a variety of hydrogen. It's radioactive, which means it breaks down spontaneously at a set rate. Have you all heard of something called a half-life? Half-life is the amount of time it takes for half of a radioactive substance to break down into something else. And tritium is kind of cool because it has a half-life of about 5.5 years. So it breaks down pretty fast. And back in the 1950s, the United States and Russia, but mostly the United States, produced massive amounts of tritium and put it into the atmosphere. You know how we did that?
What time period again?
Back in the 1950s and early 1960s.
Say how or why?
Either. However you want to answer it. Has something to do with warfare.
Arms race?
Yeah, we were testing the hydrogen bomb above ground, and it produces massive amounts of tritium. So we pumped up all this tritium into the atmosphere. And hydrogen makes up water, right? So we actually put lots of tritium into our water. And they use tritium now as kind of a forensic element to look at things like how old water is in certain areas. Anything older than 1950 really doesn't have any tritium in it. Things more recent than 1950 have lots of tritium in it. So they use this to look for counterfeit spirits and wines. A lot of wines that are very, very old, or spirits, aged scotch that they say is 100 years old, they can actually go in and test it. And they find lots of counterfeit knockoffs because stuff produced more recently than 1950, 1960 has tons of tritium in it. So you just look at the tritium levels and you can say, yeah, this was pre-1960 or post-1960. You can do it with groundwater. You can see how fast groundwater is moving through an area. How old is this water that you're sucking out of the ground? If it has tritium, then it's more recent than the 1960s. So you can use this to solve different geologic problems. So it's kind of a cool little tracer mineral that we have out in nature. Now pretty soon all the tritium that we produced in the 1960s will pretty much be gone. With a half-life of 5.5 years, we're already sort of shrinking the amount. It's been 60 years since we detonated atomic weapons above ground. So that's the number of half-lives we've gone through, but it's still measurable.
Do they do that a lot in New Mexico?
They did a lot of it in New Mexico and a lot of it in Nevada. Yeah, they did some really dumb things. They detonated one way, way, way up in the upper atmosphere, and it actually blew stuff into space.
Really?
Yeah, which they were really worried that was going to disrupt some of the protective shield that we have around the Earth that you read about in your, or that we talked about in the very first lesson that I taped for you. So we talked about this a little the other day too, about different states of matter, how atoms are arranged out in nature. We have gases, liquids, and solids. And they're defined by how the atoms move with respect to one another. In a vapor, the atoms can move relative to one another very rapidly. They're essentially not held together at all by any attractions between the atoms. They're just sort of zooming around. The air you're breathing right now. Atoms are moving all over, bouncing off the wall, bouncing off you, bouncing off the ceiling, bouncing off me. You capture a breath of that, it bounces around in your lungs. Atoms are moving rapidly and relative to one another. A liquid, they're still moving relative to one another, but they're closely packed enough so that they essentially touch and fill a confined space. So you can slosh around a glass of water and those water molecules can move relative to one another. But they're held together by little forces of attraction between the molecules that we'll talk about later. so that they're packed into a relatively confined area or confined volume. And then in solids, as long as there's any heat in the system, the atoms will still move, they'll vibrate. But they'll vibrate in fixed positions. Kind of like how you guys are right now. You're all moving, you're typing, you're writing, you're fidgeting, looking up at the ground. But you're not moving relative to one another. And isn't this great? I made that. Isn't that great?
PowerPoint?
I don't remember how I made it. This is a long time ago. But you can see the solid, right? They're not moving relative to one another. They have their own little locations that they stay in. Same neighbor to the left, same neighbor to the right. But they move a little bit. You heat them up and they'll move a little more. You heat up that solid enough and eventually the bonds break and you move into the liquid, where the atoms can still feel the forces of attraction, but they're moving fast enough that they can keep switching positions. And then in gases, they just move all over rather independently of one another. There might be small attractions out there, but for the most part, they just bounce around. Okay, two variables that affect the state of matter. And this is going to kind of launch us in actually to a discussion of Mars. We're going to talk about one of our nearby planets today. Two things that affect whether you have solids, liquids, or gases are how much heat is in your system. Because remember, heat makes atoms vibrate more rapidly. The more rapidly they vibrate, the easier it is for them to break their bonds and move from a solid state of matter to a liquid state of matter and eventually to a gas. And then the other thing that we talk about a lot in geology and maybe not some of the other sciences is pressure. Pressure is a big thing in the geologic world. When you put atoms under pressure, you force them to pack into smaller and smaller spaces. So one thing we're interested in geology, because we deal with things like rocks and minerals, magmas, water, gas coming off of magma. We talk about all these different states of matter. And we talk about how these states change from one to another. When magma cools, what does it do? When gases cool off, what do they do? When water gets cold, what does it do? So a change of state is a transformation from one of these states of matter to another. If you want to change liquid water, okay, you got a cup of water, right? If you want to change it into a solid ice, what do you do?
Freeze it.
How do you freeze it?
Stick it in the freezer.
Stick it in a freezer. Why? Because it's cold in the freezer, right? You're changing the heat. That's what you guys are used to thinking about when you talk about changing states of matter. You change the heat, right? Are you under pressure right now? Yeah, you're all under pressure. You have this big old Earth. It's got mass, right? Anything that has mass has gravity. So it's pulling down the mass in the atmosphere on top of you. So you're under pressure, but you're used to it. The only time you might experience a change in atmospheric pressure that you notice is if you drive up into the mountains. What happens?
Pressure goes down.
And how do you know, how do you feel it? What?
Ears pop.
Your ears pop, right? Pressure inside your ears, different pressure outside of your ear. So you can notice that little change in pressure, but that's probably about the only time you would really notice it as a human. But in the geologic world, we can change pressure a lot. I can dig a big hole in the backyard and throw you in it and throw dirt on top of you, right? And you're gonna feel the weight of the dirt on top of you being pulled down by gravity, right? So if I dug 2 holes in the backyard, one 2 feet deep, one 30 feet deep, buried you in it, you would feel much differently under 30 feet of dirt than you would under 2 feet of dirt. So you can change the pressure in the geologic world, and we do it all the time. So one way you could actually change states, you could keep the temperature the same, but you could alter the pressure. If you squeeze things, it tends to force those atoms together and prevent them from moving. Kind of like a clown car, you jam all these people into a small state and they wiggle around a lot, but they can't really move relative to one another. Or you can release the pressure, and that allows atoms to move more freely. So we're going to talk about some different ways we can change state, and then we're going to apply this to Mars in, I think, a really unique way. So this first possibility is one that you're used to. The pressure stays constant, kind of like what we have here on the Earth's surface, but we increase the temperature. Start with a solid, increase the temperature, atoms start vibrating more. Increase the temperature some more by adding heat, vibrates even more. Pretty soon it'll vibrate so fast that it'll start breaking bonds, turn into a liquid. One way we can think about this is with a little diagram. This is something we're going to use the rest of class today. It's really a pretty simple diagram. It's called a phase diagram. How many of you have seen phase diagrams before? A couple. Less than half of you. So what we have is this little plot. Down here, we have temperature. So on this plot, over on the left part of the graph, we have low temperature. It's cold, okay? You're over here, think cold. As you move to the right, you increase the temperature, increase the heat. It gets hotter. Over here is hot. And then on our y-axis, we have pressure. So down here, we have really low pressure. Up here, we have really high pressure. Okay? So this space right here is all the different pressure and temperature combinations that you could have out in nature. And then what we're going to put here is what the state of matter is under those combinations. So think about this for a minute. Let's say you wanted to make a gas. Okay? You want a gas. What would you do to a substance to turn it into a gas with respect to temperature and pressure? You want it cold or hot?
Hot.
Hot, because that makes the atoms move really fast. So we're going to be over here, right? What about pressure?
Low pressure,
Low, why?
so that it's got more room to do what gases do.
Yeah, you want to give it space. It wants to be free, right? They want to move around. So where is that on here? High pressure, low pressure. So we're down low and we're hot. So if you're right in here, you're probably going to be a gas, right? What if you want to make a solid?
High pressure, low temperature.
You want to lower the temperature and you want to squish the heck out of it, right? So that those atoms can't move. So if you're up here, you're probably solid, right? And if you're somewhere in the middle, you might be a liquid. So here is what a phase diagram for water looks like. Okay? So anytime you have these combinations of pressure and temperature, you're an ice cube. Okay? Anytime you have this combination of temperature and pressure, you're steam. Anytime you have this combination here in the middle, you're liquid water. You're a glass of water. Okay? Pretty simple, right? Let's take a look at how this works. What are you if you are A? You're an ice cube, right? You're solid. All right, I'm going to keep the pressure the same. So this is kind of the example where you might be home. You take an ice cube, you put it in a pan, and you put the pan on the stove, and now we're going to turn up the heat, right? So we're going to move. The pressure's going to stay the same, right? We're not altering pressure, we're just adding heat. So we're going to move from left to right, okay? So let's crank up the heat a little bit. What if I crank it up that much?
Still the same.
You're hot. You're still ice. You're just hotter ice. Maybe you've gone from -3 degrees C to -2 degrees C. Not enough to change your state, you're just warmer ice. What happens when I hit that line? What do I do?
Start to melt.
You melt, right? You change state. Melting is the process of changing something from solid to liquid, right? So we're going to melt our ice. On the Earth's surface, what temperature is that at? 0 Fahrenheit or 0 degrees C. Okay. All right. Now we've melted our ice. We're going to keep cranking up the temperature. What about if we move to here? Warmer water. What about here?
Hot water.
Hot water. All right, about there, really hot water, right? And then what happens when you hit?
Boiling water.
You boil the water. Boiling is the process of changing it from a liquid to a gas, right? So this is the melting curve right here, and this is going to be the boiling curve. Once you have steam and you keep heating it up, you just get hotter and hotter steam. Simple, right? This is one you're used to. We can go the other way though, right? Let's take some steam and cool it off. Gets cooler, cooler, cooler. What happens when it hits this line?
Condenses.
Condenses. That's the process of turning a liquid into
Gas.
or gas to a liquid, right? Okay? So it's also the condensation line. It's boiling line and it's condensation line. So that line represents changing state two different ways, from liquid to a gas, from a gas to a liquid. Okay, let's take that liquid now. We've now condensed it. It's hot. We're going to cool it off. So liquid, it's cooling, cooling, cooling. What happens at this point? It freezes. Okay? So this is not only the melting line, it's also the freezing line. Okay, that makes sense to you. You've seen that, right? You've seen that out in nature. You've seen it in your house. This is something you're familiar with. Well, let's do this a different way. Let's start with A. What are you? Solid. You're an ice cube. Now we're going to keep the temperature the same. Okay? We're going to keep the temperature the same, but we're going to crank up the pressure. What happens to ice when you crank up the pressure? It turns to liquid. Does that make sense to you? You squish it, it turns to liquid? Ice is the only natural substance that does this. It's really, really unique. When you squish it, it'll turn to a liquid, which is kind of important because this gives ice properties that we see out in nature. This is what allows glaciers to move. Think of a big, thick glacier, okay? Ice a half-mile thick. Is there a lot of pressure at the bottom? That pressure is going to cause the ice to melt some and allows it to slip. What if I put on some ice skates right now and take a running start and try to glide across the concrete floor?
Not gonna happen.
It's going to be pretty ugly, right? I'll land flat on my face. What if this was a sheet of ice?
You glide.
Why?
This is the pressure thing?
Okay, would there be pressure under my ice skate? If you don't believe me, I'll put on some ice skates. You can come lay your hand on the floor, and I will step on your hand with my ice skate. There'll be a lot of pressure, right? So what's happening to the ice right under that ice skate? It's melting, right? And I'm actually gliding over a little layer of water that reduces the friction, allows me to glide. So water is the only substance that does that. Usually this line and all other substances, and I'll put it up in a minute, kind of goes up like this, so that when you increase the pressure, it never melts. Water, this melting freezing line, kind of goes back to the left like this, and it allows you to increase the pressure and melt it. It's really, really different. So you increase the pressure, and you can melt ice. That's what most other substances look like. So if I'm anywhere in the solid field and I increase the pressure, what do I end up as? a solid. You're just squishing it more, which actually makes it more solid if you think about it that way. Every other substance other than water looks like this. So again, here's water. There's every other substance you can think of. Yeah.
In what situation in the water graph, when it changes straight from the solid to the gas?
We'll go to that next.
Okay.
Glad you asked that. Right there, right? Let's go back. What are you here? You're solid, right? What's different about that example than the previous examples?
You don't transition from solid to
We were up
liquid.
here before, right?
Yeah.
We lowered the pressure. And when we lower the pressure, what happens to water when you heat it up? Warmer ice, warmer ice, warmer ice, warmer ice. And when you hit that point, it does something called sublimation. It changes directly from a solid to a gas. Do you know of any substance that does that?
Dry ice.
Dry ice. So water in a low pressure environment, obviously not the surface of our Earth, but maybe somewhere else, does what dry ice does on Earth. So water can act like dry ice if the pressure is really low. So you sublimate it as you go from a solid to the gas. Some people call it sublimate as you go from gas to a solid, but I think the chemistry term is called deposition. Okay, so up there, that's Earth's pressure. That's why you've never seen water do that. We have too much pressure on the surface of Earth for this to happen. It does happen with dry ice. Dry ice has a different phase diagram, okay? Down there, that's where Mars is. If you go to Mars, Mars is a third the size of the Earth, okay? Is it going to have as much gravity?
No.
No. If it doesn't have as much gravity, then it's not going to be pulling an atmosphere down as much. So the pressure on the surface is much lighter. Should you see liquid water on the surface of Mars?
No.
No. That is a topographic map of Mars. All right, I want you to take just a minute. I want you to look at this really close and tell me what you see. You'll see lots of different stuff going on. You don't have to explain what you see. Just make some observations about the topography of Mars. Take a minute, write some stuff down. What observations do you note? What do you see here? I'll give you a minute or two. The longer you look at it, the more you'll see. Cool thing about Mars is we know the topography of Mars better than we know the topography of Earth. Absolute fact. We've had a satellite there since the early 1990s, just basically a big laser. And every few seconds it sends a laser down, it bounces off the surface of Mars, and the amount of time it takes for that laser to go down and come back is a function of the distance, and they can create a topographic map. The entire planet. We do not have topography this detailed of Earth because of the oceans. We don't even know the topography of some parts of the ocean very well, but we know every square inch of Mars. What do you see? What do you notice, even if you can't explain it? What looks weird or different to you here?
Lots and lots of craters.
Lots of craters. Everywhere?
Only on the higher regions.
Only in the higher regions. So you're, okay, so blue is low. Blue doesn't mean water, obviously, because there's not supposed to be liquid water on the surface of Mars, right? So this is a low area up here, and this is a high area. It's called the cratered highlands. And it's mostly in the south, right? You see many craters up here compared to down here? There's craters everywhere here, right? Not so many craters up here. Why? I can tell you that the planet through time has been hit by craters or by meteors equally everywhere. The whole planet's been bombarded by meteors. So,
Is that the water doing that then?
what water?
The H2O on the surface? Is it a liquid because of pressure?
Well, no craters up here at all, right?
Deal with the angle to the sun? No?
Because you'd have that same angle down in the south, too. The more craters, the older that surface has to be, is the assumption that geologists have made. This area down here is really old, so it's taken lots of hits. This area up here is young. It's newer stuff. So that's kind of interesting. All the new stuff is low and in the north. Okay, let's just leave that for a minute. What else do you see?
It's snow.
This here, the white is just the highest areas.
No, the.
Up here?
Yeah, is it coming into the atmosphere as gas and coming back down as snow?
That's kind of a cool idea. Probably not. The atmosphere is so thin. There is evidence that there has been some sort of snowfall, but it's just so minor because the atmosphere is so thin that it wouldn't leave enough. But that is a great idea. People have actually looked at that. What else do you see? You probably see this thing, right? This is a giant crater called Hellas Basin. It's just a big old asteroid that plunged into the planet a long time ago. And is now a big sort of depressed area. Lots of craters inside of it. So it's a really old structure. What else do you see?
Trenches, kind of.
Where?
Those scratchy marks over by the big red mountain.
Right here?
Yeah,
Yeah, look at this. What is this?
like a canyon or something.
Looks like a canyon, right? How do canyons form on Earth?
Water erosion.
Water erosion. Didn't I just tell you, though, that can't have water on Mars? Looks like water. It looks like a water carved canyon, doesn't it? Okay. What else do you see? You guys are picking out all the good stuff.
There's some round dome-ish things.
See this whole area here? This is called the Tharsis Rise. It's a bunch of volcanoes. This right here is Olympus Mons. It's the size of Colorado and it's 90,000 feet high. And you can see there are several other big volcanoes in the area. 1, 2, 3, 4, 5 huge volcanoes. And it's very high. This is 60 to 90,000 feet high. It's a big volcanic area. Kind of cool, huh? Where does this canyon start? Kind of starts up in the highlands by the volcanoes, right? So I'm going to blow up just that area a little more. So you see the cratered highlands, right? You see the Tharsis volcanoes. There's Olympus Mons. That thing is a monster. This right here is called Valles Marineris. It's the biggest canyon system in the whole solar system. The Grand Canyon would be about that big. If this were around the United States, or if this were on Earth, it would stretch all the way across the United States. Enormous canyon system. What does it look like to you? If I asked you, how did that canyon system form? What would you tell me?
Could it be from magma flow?
That was one of the ideas. They said, you know, water isn't stable on the surface. So since we have lava over here with these volcanoes, could this be carved out by magma? And that is one of the leading ideas. I don't think it's right, but there's a few people that still think that's right. So that is a very good idea. The problem with lava is that a lot of times you should find lava in the bottom of these canyons, and we've now had rovers and landers and things go in there. There's no real lava in the bottom of the canyon. In fact, what does it look like up here? Looks like a delta, doesn't it? Like a water-carved delta. Yeah.
Is water flowing under the surface?
Okay, go back to your phase diagram, right? On Mars' surface, the pressure is too low to have liquid water. Is there a place on Mars where the pressure might be high enough? Where? Under the surface. In fact, they figure if you go down 100 meters or so, there's enough pressure down there so that water could be stable. The problem is that Mars is really cold. So it's probably ice.
Are there weather patterns that correlate to that mark the trench?
There aren't.
No? Alright.
There aren't. But that's a good question. If you had ice beneath the surface, okay, and a volcano erupts through it, suddenly you now have enough heat to melt it, right? What if that massive amount of ice that you melt, all that water rushes to the surface and it starts flowing? Is it stable? No. It's not stable. What's it going to do? It's either going to, in this case, its pressure so low that it's either going to freeze right away or it's going to turn to a gas. So water rushes out, it's warm from being heated by the volcano, it's not stable, so it starts bubbling and boiling because it's changing to a gas. But as it rushes, it fills up this whole northern part of Mars. And some people think there were great oceans up here from the release of this water. They weren't around very long because the liquid water isn't stable, and the ocean would be boiling. The water would be cold. It's not hot water anymore. It's actually cold boiling water. Why is it boiling? Because it's turning to a gas in the low pressure. And it takes all that eroded material and it dumps it up here. So people have been looking for ancient shorelines and stuff along here. We have super detailed images of Mars. Look at this. Here's an image of the surface of Mars. What does that look like to you? Look like rivers, right? Probably were. Probably from water coming out of the ground. The minute it hits the surface, it's unstable. Can't remain liquid. So it either turns to ice or it boils. We have a spacecraft up there now. It's basically a neutron gun. It shoots neutrons at the surface, and when it encounters ice, the neutrons bounce back. And they found that that whole northern region, all of this blue area, is mostly ice under dirt. So it seems to fit that. You had lots of ground ice, volcanoes melted it, made these big fast floods that eroded this giant canyon. The water ponded for a while until it turned to ice or boiled away. A lot. And that's the problem with that idea is when you kind of do the math, how much water is needed to fill that north? It's a ridiculous amount. How does that happen? Have to be really long-lived eruptions. Yep. You have to have that big supply of water. So that's one of the, and that's what scientists do. They take the idea, okay, what do we, if this is lava that's causing it, what do we expect to see? And can this work? And if it's water, what can we expect to see? And can this work? And you kind of come up with the pros and cons of each, and then you go with what you feel is the best idea at the time, until you can get some more data where you can narrow it down even further. Yeah? Why does it start here rather than, say, up here?
Yeah.
Great question. Some people think that, you see this kind of area here? It's called the chaotic terrain. It's kind of rumply. People think that a lot of the deposits from the volcano have kind of filled up the canyons over time in the upper part. So the canyon may actually extend back, but it gets filled up by volcanic debris. So there's lots of studies of Mars that are going on right now to try to figure this out. But just with a little phase diagram for water and a topographic map, that's all I've given you today, you've been able to do what planetary scientists have been trying to do for decades. You can do a lot of their work with just a little basic knowledge of chemistry and some observations of a topographic map. You can do some pretty cool stuff. See, you all did science today. It's all scientists do. Take the available data and try to weave a story that makes sense out of it. Okay. So just to kind of summarize what you guys pointed out, is there is a lot of visual evidence that water flowed on Mars' surface. The other possibility we didn't talk about, and it's an idea, right now there's a big debate. Did Mars ever have a big atmosphere or not? One idea is that maybe Mars had a lot of surface pressure because it had a thick atmosphere one day in the past. Where would that atmosphere have come from? Probably all those erupting volcanoes. Think of all the gas that those erupting volcanoes would have given off. So the idea that some have is that maybe Mars had an extensive atmosphere in the past that would create enough pressure that would allow water to be stable. Mars is a smaller planet. The volcanoes died off a long time ago, and Mars lost its atmosphere since then. That's one idea. Some people think, no, Mars has always been this sort of dry, cold, climateless place, and water may have formed underground as volcanoes erupted through this great ice sheet. A really good friend of mine studies Mars, and this is what he believes. He believes that Mars was once warm and wet. In fact, he even goes a step farther. He said not only is Mars warm and wet in its early history, it had life. And we actually have meteors that have landed on Earth that definitely came from Mars. There's no other body in the solar system that has the same rocks that Mars has, and we find meteors that have that rock type. So he believes that life may have been transported from Mars to Earth on these little chunks of rocks that were blasted off Mars' surface when meteors hit. So a meteor would hit Mars, throw a bunch of these rocks up. The rocks then drift around in space. They have little microbes on it. They land on Earth, and Mars populates Earth with life. That's his idea. It's kind of wild. Religious people hate him. But, you know, it's within the realm of possibility given what we know about the solar system. I don't think he's right, but it's an idea that's out there. Kind of cool. And now we've probably polluted Mars because we've sent several space probes that no doubt have microbes that were from Earth that were brought along for the ride to Mars. So we're sort of cross-contaminating planets with life forms. Interesting idea. All right, any questions on that?